So the 4 assumptions throughout this class are small strains, small deformations, a linear stress-strain relationship, homogeneous materials, and isotropic materials. And isotropic means that no matter how the material is oriented compared to your coordinate system, the material behaviors are the same. Okay, so any direction, the material behaviors are the same. The material's no weaker or stronger along one axis than another axis. And with these 4 assumptions, we get this constitutive relationship between stress and strain. That says the Voigt strain is equal to this compliance matrix that is, well, so the Voigt strain is, a 6x1. And that's equal to this compliance matrix that's 1 over E, negative nu over E, negative nu over E, 0, 0, 0. And then keep moving the 1 over E along. And then for the last 3 rows, the thing that moves along is just this 2 times the quantity 1 plus nu over E. And you multiply that by the Voigt stress. Okay, so all 4 of those requirements are necessary in order to have this relationship. If you multiply this out, so remember that the Voigt, maybe I should have just put this in that equation above, but the Voigt strain is XX, YY, ZZ, and then the shear strains are represented with that gamma, and we have YZ, XZ, and XY. For the shear strain, for the shear strains, you have to use these different variables. These gammas are different than those epsilons because this is sort of a pain, but there's another way to measure strain that you call epsilons. So the way we're doing it is this. Okay, has to be that. With stress, though, there's a little wiggle room. So the Voigt stress is sigma XX, sigma YY, ZZ. And then you can write it, keep writing sigmas. So YZ, xz, xy. And that means the exact same thing as, so the first three are still sigmas. But the shear stresses are often written as taus. Okay. So these mean the same thing. These, if you write those as epsilons, it means something different. Okay. Well, what does this mean if you multiply this matrix out? So if you multiply the compliance matrix to the Voigt stress, these are the relationships you get. Exx is equal to 1 over E times sigma xx minus nu over E times sigma yy minus nu over E times sigma zz, and nothing else. Eyy is negative nu over E times sigma xx plus 1 over E times sigma yy minus nu over E times sigma zz. And EZZ is negative nu over E sigma xx minus nu over E times sigma yy plus 1 over E times sigma zz. Okay, so those are the first, so we have 6 of these equations that come from that one single matrix equation. These first 3 tell us that normal strains depend on all the normal stresses. Physically, does that make sense? So that's saying if you're measuring, say, the deformation along the x-axis, does it make sense that that is affected by not just the loading along the x-axis, but also the loading along the y and z-axis? What that's including there is that bulging slash contracting effect that I was talking about. If you stretch something, it gets skinnier. If you compress something, it bulges out on the sides. Okay, so it's that Poisson's effect. That's what you measure with the Poisson's ratio. So if you're measuring the deformation in this direction, okay, and you compress it down in this direction, the deformation is going to be affected. Okay, so that's true for along every axis for normal strains. Okay. Now what about the shear strains? So if you're measuring the YZ shear strain, that only depends on one shear stress, only the associated one. So this is equal to 2 times the quantity 1 plus nu over E times tau YZ. Okay, so there's no equivalent thing to the Poisson's effect for shear stresses and strains. The XZ shear strain is equal to 2 times the quantity 1 plus nu over E tau XZ. And XY is equal to 2 times the quantity 1 plus nu over E times tau XY. So the shear strains is only affected by the associated shear stress. This is sort of the first glimpse, well, one of the first glimpses of, so the way that we're doing this class mathematically, we're going to do all the same calculations that you would do in the textbook and that the traditional way that you do the calculations in this class. So we'll be able to calculate all the same stuff. But traditionally, everything is just done as scalar equations. And so instead of doing things in terms of matrices and stuff, you're just given these 6 equations, okay? And then when we get to stress transformations, you'll have all these different equations where it's not super clear where the things come from. But to me, it makes a million times more sense to see like where these equations come from. It comes from that matrix relationship. So yeah, this is a place where if you look at a textbook, like the textbook they use at the U or whatever, you'd see these equations. Instead of that, we're going to do everything this way. But it's nice to see the dependence of the individual values. All right, so let's do an example problem with a tensor test. So let's say we have this material sample. So say, this is like some new alloy of metal or something, and we want to take a measurement to measure the relationship between the stress and the strain. So let's say that on each end we put 5,000 newtons of force. So we put this thing into 5,000 newtons of tension. And we're going to use a coordinate system. For this, we'll always use a coordinate system where the x-axis is along the long axis. Other than that, it doesn't matter which way the axes point. So let's call this x, this y, and this z. And before the deformation, the length is 0.1 meters, so 10 centimeters. And the thickness is 1 centimeter, so 0.01 meters. And the width of the side is 2 centimeters, so 0.02 meters. Let me move that over. Okay. And if you apply this force and then very carefully measure the changes in those side lengths, we get that under the load, when the load is applied, the lengths, I guess I'm calling this lowercase l, so L becomes 0.10003. And I'm going to call this the width, W. Since we're stretching along the x-axis, along the y-axis, it's going to get smaller. So this is 0.00, and then 4 9s and a 2. And by the way, so the way I have it set up in this is that we're measuring the change in length of that thickness, okay? But because it's isotropic and this thing has the same material properties in every direction, we could have instead measured that width and we'd get the exact same answers, okay? So it doesn't matter which one of these two out-of-axis measurements you take, you'll get the same answer for E and Poisson's ratio. And so we want to do this. First, we want to find the compliance matrix. And then second, if this material, you know, this type of material, what we're testing, has a stress tensor at some point of (2 times 10 to the 7th, -1 times 10 to the 7th, 0, -1 times 10 to the 7th, 0, 0, and then 0, 0, 8 times 10 to the 6. And this is Pascal's. What's the strain? So the idea here is we're going to do this one very simple test with one piece of, you know, say you do this for steel. So you do this test for your particular composition of steel, and you get some numbers that let you fill in the compliance matrix. And then later, you do calculations for the piece of steel that you have holding up a part of a building or whatever. It's a totally different shape, totally different loads, okay? And if you calculate that that's going to be the stress, now you can use the compliance matrix you got from this simple test to calculate what the strain is going to be, to approximate what the deformation is going to be. Okay, so that's what we're doing here. There doesn't have to be any relationship between the shape or the loading of this and the shape or the loading of that, as long as it's the same material. All right, so for part A, the XX stress is 5,000 divided by the cross-sectional area, So the cross-sectional area here is the 1 centimeter times the 2 centimeters. Are you with me on that? We're talking about this area here. Okay. So 5,000 divided by 0.01 times 0.02, and you get a value of definitely something. 83.3 repeating times 10 to the 9th. I'm using the right stuff. What did you get? Oh, okay. Okay, yes. 2.5 times 10 to the 7th pascals. And then we'll measure the strain along the x-axis, the normal strain. And that is the deformed length of 0.1, 1, 2, 3 zeros, and a 3 minus 0.1 divided by 0.1 and you get 3.0 times 10 to the minus 4, and that's unitless. And then in the y direction, EYY is the deformed thickness, which is 0.00, then 4 nines and a 2, minus 0.01 divided by 0.01, and you get negative 8.0 times 10 to the minus 5th. So then Young's modulus is sigma xx over exx. So 2.5 times 10 to the 7th pascals divided by 3.0 times 10 to the minus 4. And you get an E value of 83.3 repeating times 10 to the 9 pascals. 83.3 repeating gigapascals. And the Poisson's ratio is negative out of axis strain. So that's the 8.0 times 10 to the minus 5th divided by, we have a negative here, divided by the in-axis strain of 3.0 times 10 to the minus 4. The negatives cancel out, and you get a positive Poisson's ratio. You always need to get something between 0 and 0.5, and in this case, it's 0.26 repeating, and that's unitless. And now that we have E and new, we can fill out the compliance matrix that represents this, our type of, well, this wouldn't be steel, by the way. Steel would have a value of about 200 gigapascals. This is a softer metal. That's not too far off like copper. But so now that we have that for copper, we can fill out the compliance matrix, and then we can use that for whatever we shape this copper into, you know, make it into thin tube things or make it into a big chunk. This compliance matrix will represent it no matter what. So the compliance matrix with these values is 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, and then 0, 0, 0. And then just keep moving the 1.2 times 10 to the minus 11 along. And then 0 in the shear spots. So now we're done with those normal stresses, those normal rows. So the next three all have zeros in the normal spots. And then 3.05 times 10 to the minus 11. That keeps moving down diagonally. And the units are 1 over pascals, the way I have it. And you do need to keep track of those units because it's really easy to mismatch your units, and then you're off by usually at least a factor of 1,000. And if you're off on a calculation by a factor of 1,000 or more, your calculations are not very good.
Is an okay way to tell the units by, like, if it's a really, really small number for a really big number, like, would that be okay?
Not the units. That's an okay way to tell whether it's a compliance or a stiffness matrix, but the way to tell the units is just to look at what you're using here. We calculated this stress in pascals. This is unitless, and that means that E has to be in pascals, and that means that the compliance matrix is 1 over pascals. Any questions yet? Okay, so now we're going to part B. And we have this stress tensor. So now a whole different part of the company has formed hollow tubes out of this type of copper, whatever it is. And it's under some loads, and they calculate that those loads at some point in the material are producing a stress of 2 times 10 to the 7, negative 1 times 10 to the 7, 0, negative 1 times 10 to the 7, 0, 0, and 0, 0, and positive 8 times 10 to the 6 in pascals. Well, in order to figure out the strain, we need the Voigt stress. So this stress tensor in Voigt form is 2 times 10 to the 7, 0, 8 times 10 to the 6, and then yz, xz, xy. And now to calculate the strain, we're just going to multiply that compliance matrix by the Voigt stress. And what you get in this case is 0.30214. So that's the XX normal strain. Then the second one is negative 0.40896. Then the ZZ normal strain is 0.40, and then 32, and then 0, 0, negative 3 zeros, and then 304. Does it make sense that we have a 0 value, that we could have a 0 value for the YY normal stress and a non-zero value for the YY normal strain? Yeah, it's because of that Poisson's effect. Okay, it's because these normal strains are dependent on every normal stress, not just the associated one. Okay, but that's not true with the shear strains, and so that's why you see the places where we have 0 shear stress, we also have 0 shear strain. And so at this point, we have elongation along the x-axis. Okay, it's stretching along the x-axis. We have contraction along the y-axis, elongation along the z-axis. Now the angle between the y and the positive y face and the positive z face stays the same. That angle stays the same. Between the x face and the z face, positive, stays the same. And between the positive x and the positive y face, we have a negative shear strain, so it's getting more obtuse. Okay, so you could sketch that out and get a sense for like, okay, it's bigger this way, smaller this way, bent this way. Okay. Okay, we have this at one point out of a whole copper tube. So how many more points do we have to do this to represent the whole tube? We've gotten one taken care of, but there's infinitely many points. So we haven't really gotten any closer. So anyways, you just remember that this represents a single point. Okay. And if you want to represent the whole thing, you need to represent these functionally somehow. You know, come up with functions to see how these values are varying. Dallas, do you have a question?
Sorry.
Okay.
So like this second part B, that's not in relation to the stretching on
Right.
Okay.
That's right. It's a totally different, yeah, in a different country or whatever, they're doing this. We sent them our values for E and nu, and then based on that, they can do whatever they want with that metal and use that compliance matrix. Yep.
Coordinate system that you gave us, that applies to all problems that we have.
For the tensile tests, that's the way to probably do it, yeah. I mean, you don't have to do it that way. You could do it in any coordinate system, but it's sort of easier to do it the same every time.
Okay, because so you always want to measure the length of it plus just a little width.
Yeah.
Okay.
Yeah.
So then the subscripts for those for the equations they don't really matter too much. Or
It,
X, Y,
right. It doesn't have to be those subscripts. It just has to be the axis that's being stretched versus some axis that's not, that's perpendicular to that.
You're not doing this exact thing. You just set the x-axis in the direction of
So for the tensile test, people normally take the x-axis to be along the loading axis.
Right, yeah. Okay.
But outside of the tensile test, it doesn't matter what coordinate system you use. The Young's modulus and the Poisson's ratio hold no matter what crazy, no matter what the shape of the thing is and no matter where you put your axes.
Just for the homework, is the Z and the Y is split.
Mm-hmm.
I just thought it was kind of.
Yeah, right. So all that matters is loading versus not loaded for the tensile test. But I always put my x-axis along the loading axis.